Today, we are proving the fundamental theorem of calculus 2.0. Let's review 1.0 first, right? Because you have to kind of remember what 1.0 was before we can do 2.0. So this is fundamental theorem of calculus 1.0. What does it state? Okay, if you have, in a sense, this is it, the important one. If you have integral of f of, let's call it x, from a to b, this is same as antiderivative evaluated f minus antiderivative evaluated at a, right? Where df over dx is equal to f. And so that thing tells you that capital F is just the antiderivative. So this thing only cares about the boundary endpoint. You know what I'm saying? A and B. Yeah, I know this like very, the most significant theorem in the history of mathematics. Remember this one? Yeah, and you should remember the proof of it too, but hey. Okay, then now 2.0. What does the 2.0 states? Okay, here's a 2.0. Remember line integral? F dot dr? This thingy, right? Okay, and I'm gonna sketch this thing for you. Say that curve looks like that. This is where t is equal to a, and this is t is equal to b. So this is the curve C. You know what I'm saying? This thingy is equal to lowercase f, and then like we're switching the notation. Lowercase f is the antiderivative of capital F evaluated at t is equal to b minus lowercase f antiderivative at a. That's it. What? Really? So it's the same idea now, isn't it? Where, or it's if and only if, this thing comes with a huge condition, and that if and only if is this thing exists. Gradient of some f is equal to your vector field f. So it's exactly the same thing as this thing. You know what I'm saying? Because the derivative of, antiderivative of this f, it's like, what's an antiderivative, right? Because we have x, y, and z variable. So how do you take a derivative? Well, gradient of some function. You get it? So this thing is kind of known as a potential function. Wait, where are you in physics class? Have you done potential yet? Not the potential energy, but the potential, ENN? Wait, are you doing ENN?
I mean, students are self-studying because you're not teaching it with mechanics this year. So.
Okay, but you know what potential function kind of is, right? Yeah, this is a potential function. If you take a derivative with respect to space, meaning x, y, and z variable, that's what gradient is. You remember gradient, right? And then you get the vector field. So if you take a gradient of gravitational potential function, you get gravitational field. If you take the electric potential function V gradient, then you get electric field, and so on. You get it? If that thing exists, and this may or may not exist, only condition that this thing exists is if the force is conservative. Okay, it doesn't always exist. Just like in this case, that antiderivative has to exist. If it doesn't exist, we can't do that anymore. Then we are stuck with the Riemann sum. You get it? So same idea. One way we can bypass this line integral and just evaluate the endpoint is this potential function has to exist. And let me tell you what that gradient is. Gradient, once again, reminder, that thingy is I vector times with respect to x, j vector times derivative with respect to y, plus k vector times derivative with respect to z. This is what gradient. So derivative with respect to space, all three. Good. Dang, huh? That's some statement now, isn't it? Shall we prove it? Yes, we shall, because this is a big deal. Okay, and then I'm gonna give you the technique of how to verify if the force field is conservative even, right? I'll do that in an example. But let's just see if that thing exists. So here's a proof. Okay. So let's start with this. Integral of f dot dr. Okay. So assuming this thing exists, I can replace it with a gradient of lowercase f. And if you take a gradient of something, this is not a vector function. This is just 3 variable scalar function, if you will. Gradient converts into a vector, right? That's why this side is a vector. Oh, arrow. And this side, only the gradient is a vector. And some people don't like that notation, but hey, use it. And so this dot product makes sense, right? So far, so good. Okay, let's take a gradient and see what happens. So this is over C. Okay, so this is still over C. Gradient is that thing with f, right? So what we get is partial of f with respect to x. I'm gonna zoom in a little bit, I'm writing tiny. I vector plus partial of f with respect to y times j vector plus partial of f with respect to z k vector, isn't it? So far so good. And then dot it with, I now have to figure out what dr is. So let's say this is r, vector function of t, and of course it has x, function of t, I vector plus y, function of t, j vector plus z, function of t, k vector, correct? Say yes. So if I take a, derivative of this, dr over dt, that will be, this is not the regular derivative, dx over dt, I vector plus dy over dt, j vector plus dz over dt, k vector now, isn't it? Say yes. So that goes in here. So I have dx over dt, I vector plus dy over dt, j vector plus dz over dt, k vector, and then dt now. You with me? Say yes. Let's dot these two. So how do we take a dot product now? Well, multiply the i's together, j's together, and k's together. So we have partial f, partial x, dx dt, plus, and we add them up. So partial f, partial y, dy over dt, and then plus partial f, partial z, dz over dt, eh? And dt. Now we have successfully converted this thing from A to B, because now it's all in terms of t. We could have put it here, but whatever. You with me? Do you remember what that thingy was? What is that thingy inside the integral? That sure looks like chain rule now, doesn't it? Wasn't that df over dt? Is that how we evaluate chain rule? You have to search your feelings, you know it's true. You know what I'm saying? Wait, you have integral of the derivative. So, well, this fundamental theorem applies now. So this thingy just is antiderivative of that, of course, is this, evaluated B, minus this, evaluated A. Bang. Amazing, isn't it? Right. Okay, shall we take an example? Yeah, that was heavy. Let's take an example. Okay, example is we need to evaluate this. F dot dr. Okay, and my F looks like this. Let's say y square I vector plus 2xy plus e to the 3 z vector, okay, plus 3y, oh, j vector plus 3y e to the 3 z k vector. Dang, huh? Now that's handful, isn't it? And we don't even know what C is. So we have to evaluate this along any path. We'll just say do that from t is equal to 0 to t is equal to 1 along any path, any unknown path. Dang, huh? Shall we do it? Okay, now let's just say the gradient exists, okay? So first, let's suppose this thing exists. Right? Because if it doesn't exist, then we can't do it, right? How we have to verify this is the case, right? So your vector field, this thingy, remember, looks like this. Right? Suppose this exists. What that tells you is we have this F, right? Then this thingy better be this one, and this thingy better be this one, and this thingy better be this one, right? That's what that means. Good? IJK? Okay, so let's just think about this. I'm gonna write that down here. So partial f, partial x is equal to y squared. Good. And then partial f, partial y is equal to 2xy plus e to the 3z. And partial f, partial z is equal to 3y e to the 3z, okay? And we'll take second derivative, okay? I'll only do one, you guys do the rest of them. Let's say partial f, and then we have this, but if I take another derivative, what does that become? Do you see this is 2y, right? So I took a derivative with respect to x first, And then now I'm taking, when that's given to y, I'm gonna take a derivative with respect to y. Good? Say yes. Now I'm gonna compare that with this thingy, derivative with respect to x. Okay, let's see. So I'm gonna differentiate this with respect to x, then I get 2y. So these two are the same thing, right? And then we have to do that to all of it. So there are 6 different combinations. You have to check all the cross second derivatives. And if you do that, then you say this is conservative. But my question is, why does that prove that this field is conservative in the first place? Why? I mean, that's what you're supposed to do, but why are you supposed to do such a thing? That is because if this thing exists, right? We are saying our f is some gradient of potential function. If that exists, and if that thing, so any function, if you take a cross derivative with respect to x, then y, versus with respect to y, then x, you have to get the same thing. If that thingy does not exist, then of course this bets are off, right? There's no reason for these two to be the same thing. Did you get that part? Good? Yeah, so everything has to do with this assumption that such a thing exists. For example, your tornado vector field, there's no such a function because it's not conservative. You get it? Conservative meaning this thing exists. Potential function. Okay, so assuming you got that part, okay, now, then we have to find this thingy, right? Okay, I'm gonna copy this part and reuse it. So let's go out and find this f. Okay, I'm gonna change the color. So this, I'm gonna take an antiderivative of this thing with respect to x, okay? Because that's a derivative with respect to x, so I'm gonna integrate. So f, x, y, z, whatever, should be x times y squared plus constant, eh? Plus constant. Are we good? Why do you guys look lost? It's just simple antiderivative with respect to x. However, this constant is not truly a constant. Don't you hate when your teacher writes something and when you're done copying it and he erases it? This might have some y and z variable in it. It's not a true constant. It's only constant with respect to x variable. You get it? Because then if you take a derivative with respect to x, this entire thing dies and we get y squared back. So far, so good. Now I'm going to take a derivative of this thing with respect to y. Okay, so this first term becomes 2xy, and this thingy becomes partial derivative of g with respect to y now, doesn't it? Say yes. Now I'm going to compare this thingy with that thingy, right? Partial f, partial y, partial f, partial y, they better be the same thing, eh? So that tells you your partial g over partial y is equal to e to the 3z, eh? You got that much? You with me? Okay, I'm going to take an antiderivative of this now. So g, we remember, was a function of y and z. So if I take an antiderivative of this with respect to y, I just pick up y and e to the 3z, right? Plus another constant. But this time, that constant, I'll just call it A, K, H, and K. That thing might have some Z variable in it. It's just constant with respect to X and Y now. You get it? Let's review. If I differentiate this thing with respect to Y, this thing gives you that, and this dies. You with me? Right, let's plug it back in now. So, remember my F. My F is this, right? So my F, X, Y, Z is equal to XY squared plus G, but I kind of know what part of G is. It's Y e to the 3Z plus some constant function only with Z variable in it. Guess what I'm going to do now? I'm going to differentiate this with respect to Z. So partial F, partial Z, this whole thing dies. This thing becomes 3y e to the 3z. With me? Say yes. And this thingy, of course, is dk over dz now, right? Because it still might have some z in it. Good? Say yes. Now I'm comparing this thingy with that thingy over there. Right? Oh, that thingy does not have this thing, so this must be 0, eh? So that thingy tells you dk over dz is equal to 0, right? Which really tells you this is just true constant, right? K, which may or may not have variable z in it, is really just c. Good? Say yes. Are you with me or are you lost? Now is a good time to let me know. Your superpositional state between understanding it and not understanding it, kind of like Schrodinger's cat. So only way to figure out whether you understood it or not understood is to take a test to realize you didn't understand it after all. That's like opening the box. Okay. There's a video. So that xyz now is equal to, from this line, x y squared plus y e to the 3z plus, this is just true constant c. You with me? We can check and find the partial derivatives with respect to x, then you have y squared there. With respect to y, so 2xy here, and that thingy, y dies, so that right there. With respect to z, this dies, and this thingy, 3y z to the 3z. You get it? We just found that antiderivative. Well then, only one thing left now, right? Remember this? F dot dr. Right? And this thing is f of whatever the xy, and we don't know what that is, right? Let's say evaluated at t is equal to 1 minus f of xyz, that thingy, because we don't know the vector function itself, right? So as soon as we're given a vector function, we'll evaluate x, y, z when t is equal to 0 and t is equal to 1 and plug it in and we're done. You get it?